Hello students, welcome to this lecture number 11 on ionic equilibrium. In this lecture we will be going to discuss a very important thing in this subject, that is in the ionic equilibrium subject, that is the solubility of the ionic solids and its solubility product, and this will be the last subject that we are going to touch in this lecture. So in this lecture we will be going to discuss this very important thing, that is the solubility and the solubility product of the sparingly soluble salts. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. Solubility of the ionic solids varies a great deal. You can observe that calcium chloride is a very much soluble in water, and it is so soluble that it will absorb moisture from the atmosphere, and it is called a hygroscopic material. Whereas the lithium fluoride, the same ionic compound, having the very little solubility in the water. So there is, you can see, lot of variations in terms of solubility of the ionic solids. And why it is so? The main reason behind these two things: number one, the lattice enthalpy. Influence the solubility of sparingly soluble salts. When it is observed the solvation enthalpy is higher than the lattice enthalpy, then the salt is going to be dissolved in the water, because at that time what is going to happen, lattice enthalpy is basically the attractive forces. It correlates with the attractive forces of the cations and ions in the ionic solids. And when the solvation enthalpy is higher than the lattice enthalpy, then it will be able to break all the attractive forces between these cation and anions, and it will ultimately dissolve in the water. So that is the reason why it is so, that its solubility is different from the different molecules, and that will depends on this very important factor. Now, the solubility of the ionic solids can be categorized in the three ways. There are basically three categories. You can see that category 1, is the soluble. Category 1 is soluble, and the solubility will be greater than 0.1 mole. When this solid A have the solubility of greater than 0.1 mole, we will say that solid is soluble. Then category 2 is given, that is the non-soluble. Non-soluble means when its solubility ranging from 0.01 mole to 0.1 mole. And another thing, that is the category 3. Category 3 is sparingly soluble salt. Sparingly soluble salt is sparingly soluble salt. Their solubility is less than 0.01 mole. So we can see there is a three type of solubility and regard to the ionic solids. That is, first one when it has solid 0.1 mole, and second is 0.01 mole to 0.1 mole, and last, that is less than 0.01 mole, that is a very little amount of solubility of salts, and this is called the Sparingly soluble salts. In this lecture we will going to discuss the solubility and solubility product of these Sparingly soluble salts, and for that let us take the example of a Sparingly soluble salts BaSO4, which is in equilibrium with its saturated solutions. So we can write this dissociation of the BaSO4 in the water in the saturated solution. You can see that is in a saturated solution, that it with the equilibrium which is dissolved ions, which is dissociated ions with Ba plus 2 and SO2 minus saturated solution. This is the equation for the, and it will make a equilibrium with its ions, saturated ion between the ions in the saturated solutions, and it is insoluble BaSO4. So there will be the equilibrium between this. Now we can write the equilibrium constant as per the law of chemical equilibrium. K is basically the molar concentration that we already studied, molar concentration of this BaSO4, Ba2 ions and the SO4 2 minus ions, and this is the BaSO4, molar concentration of BaSO4. And we know this is a pure solid that its molar concentration do not change. So we can assume, we can consider BaSO4 solid as a constant term. So its molar concentration do not change. So we include this BaSO4, concentration of BaSO4, molar concentration of BaSO4 as a constant in the constant equilibrium constant, and it will give a new equilibrium constant, that is the solubility product. S means solubility, P means product, solubility product constant, and it will be, you see, like this. So it is like this. So what is the definition of the product, solubility product of these Sparingly soluble salts? So we can write KSP is basically the solubility product. Solubility product constant, or we can say solubility product, that is the KSP. And that is, you can see how do we define its solubility product. We can define the solubility product. It is basically the product of the molar concentration of the ions in the saturated solution at a given temperature, because if temperature change, then the dissociation constant will change and it will going to dissociate different numbers of ions. So at a given temperature, the product of the molar concentration of these ions in the saturated solutions raised to the power the number of ions that is produced from a one molecule. See here, it is only one ions, one Ba2 plus ion and one SO4 2 minus ion produced. So there is only, you can say this is 1 and this is 1. But if you see this equation, PbCl2. PbCl2, what will be the product constant? That you can see Pb plus 2 plus 2Cl minus. So in this case, what will be solubility product? Ksp. Ksp is, you can write, molar concentration of Pb2 plus and the molar concentration of Cl minus, that is whole square. So in this is basically the solubility product, and we can have the different type. For the different type of solids, we have the different type of product, solubility product constant. So this is what the solubility product constant is. It is basically the product of the molar concentration of the ions and raised to the power their number of ions produced from a one molecule. This is called the solubility product constant, or we can say solubility product. So another thing that we are going to discuss, that is the ionic product. What is ionic product? Ionic product is basically the, you can able to have this product of the ions in the solutions. It may be saturated solution or it may not be saturated solution. It is also, you can write, it is also a product of molar concentration, product of molar concentration of ions in the saturated solution, in the saturated solution at any time. At any time means it may be saturated or it may be unsaturated at any time. So it is the product of molar concentration at the equilibrium, when the reaction has, we can also write, when the reaction has achieved the equilibrium, then the Ksp is equal to the ionic product. So you can write this Ksp is Isp, that is ionic product. So you can have this data. Now we are going to discuss another important thing, that is the common ion effect. Common ion effect. What is common ion effect? It is basically when we put some strong electrolytes in a weak electrolyte solution, aqueous solution of the weak electrolytes, what we find, a very important thing, that the dissociation, or you can say ionization, of these weak electrolytes has been suppressed. As for example, you can see, suppose this is acetic acid. Acetic acid is a weak electrolyte and it is dissociated like this way. It will produce acetate ion and H plus ion. When we put some strong electrolytes, that is sodium acetate, when we put sodium acetate being a strong electrolyte, it will completely dissociate into its ions, right? So what is going to happen? There will be the common ions, that is here it is an anion, common ions. So what is going to happen? You can think we can consider the L-11 principle. What it says, when the concentration of any of the product or any of the reactant has increased, the reaction will proceed in that direction where this introduced product or introduced reaction will be consumed. So what is here? We are putting this concentration, when we are giving this CH3COONA, then concentration of acetate ion has increased. When the concentration of acetate ion increase, then this reaction will goes on the reverse direction. When it will be goes on the reverse direction, then what will going to happen? Now the dissociation, or you can say ionization of the acetic acid will be suppressed, and that is called the common ion effect. Due to this common ion, what is going to happen? There is the dissociation or ionization of the acetic acid has been suppressed. And this is a very important factor, important thing in chemistry, and with the help of this common ion effect, lot of industrial activities has been done. That we will discuss later on. Okay, so we understand what is common ion effect. Now we are going to understand different types of application of solubility product. Application of number 1, that determination of the solubility. Determination of solubility. Solubility of Sparingly soluble salt. Of Sparingly soluble salt. So what is how we can determine this? So let us take an example of a calcium phosphate. This is a Sparingly soluble salt, and when it is dissociated, it will produce this. So you can see from this one molecule of calcium phosphate, you have these 3 calcium ions and 2 phosphate ions. Two calcium ions and 3 calcium ions and 2 phosphate ions. Suppose the solubility of the calcium phosphate is S mole per liter. So it will going to ionize and produce the 3S molar solution of Ca2 plus and 2S molar solution of this plus. So what is the solubility product? Solubility product is, suppose we are taking here solubility product, we know that Ksp is given by the concentration of Ca plus 2 ion whole cube into PO4 3 minus, that is whole square. So what is this? Is 3S and it is 2S the whole square. So in again get that is 27 into that is 8, and you get S to the power 5. Right? So S is coming around 1 by 27 into 8 into Ksp into Ksp to the power 1 by 5. So if we know this Ksp, we can able to calculate the solubility of the calcium phosphate, and that is how we can able to calculate the solubility of this any Sparingly soluble salts. Okay, so this will be coming around, if we take this 27 into 8, around 1 by 108 into Ksp. So this is the one of the most important application for the solubility product. Next application, that is prediction of precipitation Suppose there is a two solutions have been mixed. From these two solutions, which solution will be material soluble, Sparingly soluble salts is going to be precipitate? That can be easily determined from the KSP. When KSP, that is a solubility product, and this how the we can able to predict when the ionic product is greater than the solubility product, ionic product greater than the KSP, then there will be the precipitation, PPT. And when ionic product less than the KSP, then there will be no PPT, precipitation. There will be no precipitation. So in this way we can able to calculate we can able to determine the precipitation when there is the two solution has been mixed. That is the second application. Third application, that is the salting out of salt. Salting out of salt. When soap, suppose this is a soap and we have given some NaCl, what is going to happen? The reaction due to the common ion effect is a common ion Na plus and this is a Na plus. The reaction will goes on the reverse direction and the soap will be crystallizes out. So this is another thing, that is salting out of the soap. And fourth thing, that purification of the solids, purification of common salt. How do we purify? We have to pass, if we pass the HCl gas through this solution of NaCl, then what is going to happen? The reverse direction, the reaction will goes on in this way. That is the dissociation of NaCl, and when we pass the HCl, it will have H plus and Cl minus ion. And this Cl minus ion, this is a common ion. Due to this presence of the common ion, is a higher concentration. So for the large Achilles principle, we can able to understand that the reverse reaction will be going on. So there will be the crystallization of NaCl, and at that time we will get the most purified common salt. Okay, so by application of this common salt, common ion effect, we can able to give this purification. We can able to purify the common salt very easily. So that is all the application of the solubility product. Now we do some numerical. This is a question that I have given, that solubility product constant of three type of salts is given here. Mx, it is have the solubility product constant this, Mx2 is this, Mx3 is this. So you have to say the order of solubility, and order of solubility is given. There is the fourth option and you have to choose which of the right answer. For this, first you have to calculate the solubility of this salt from its solubility product. So for MX salt, what will be solubility product? Solubility that we have to see, that is dissociation with like this. So this is suppose solubility, this is S and this is S. So we get the Ksp is equal to S square. Now it is given, that is 4 into 10 to the power minus 8. So we get that 2 into 10 to the power minus 4. That is for Mx. The solubility of Mx is this. And for Mx2, we can write its equation is like this way. M2 plus 2x minus. So its solubility Ksp, it is given. What is it given? This is given 3.2 into 10 to the power minus 14. So from this we can get, suppose this is S, so this will be S and 2S. So we get S into 2S whole square is equal to 3.2 into 10 to the power minus 10 to the minus 14. So we get 4S3 is equal to 3.2 into 10 to the power minus 14. So we get here S equal to, we get point, if we calculate this, root over 1 by 3, 3.2, and it will be coming around, so just writing down the result. That will be 2 into 10 to the power minus 5. Okay, so this will be the solubility of this. And now MX3 this is M3X suppose. Then we will get 3M plus and minus. So its solubility, suppose is S, this will be 3S and this will be S. So 3S whole cube into S is equal to, we are getting it 2.7 in 10 to the power minus 15. So we get 3S to the power 4, 3, that's 27. It will be 27 S to the power 4. This will be coming around 2.7 into 10 to the power minus 15. The 27 will cut and it will give in S is equal to, we will get 10 to the power minus 4. So we get the solubility of this Mx is this, solubility product of Mx2 is this, and solubility product of this is coming out 10 to the power 4. So from this we can easily able to say that the solubility of the Mx is the highest. It is followed by M3X is 10 to the power 4 and Mx2 is the 10 to the power 5. minus 2 into 10 to the minus 5. So D option will be the correct answer. So in this way we can, by taking the help of this solubility product constant, you can able to know the solubility of the Sparingly sulfate salts. Product of MOH is 1 into 10 to the power minus 10 mole square, and these units, and pH of the solution will be, we have to calculate the pH of the solution from this solubility product. So for that we have to write first the ionization equation. Solubility, suppose solubility is S, so it will produce S moles of M plus S moles of OH minus. So we will know KSP is equal to A square, and A square is given here 1 into 10 to the power minus 10. So we get the S is equal to 1 into 10 to the power minus 5, and that will be the concentration, molar concentration of OH minus ion. We know the ionic product of water is 10 to the power minus 14. 10 to the power minus 14. So we get pH means hydrogen ion concentration, which 10 to the power minus 14 divided by 10 to the power minus 5. So we will get 10 to the power minus 9. So pH is what? Minus log of H plus ion concentration. So we put, it will give 9. So B is the right answer. Okay. In this way, from the solubility product, you can also able to calculate the pH of the solutions. Okay. This is another very good question, that in saturated solution of the Sparingly soluble salts, AgIO3 molar weight of this salt is 283 given. The equilibrium sets in, this is the equilibrium has been achieved by this salt in the aqueous solution, and its KSP is given. You have to find out what is the mass of the AgIO3 in the 100 milliliter of solutions. So what we will do, from the solubility product we can able to calculate the solubility of this, solubility of AgIO3. Then we will, from this solubility it will produce the same number ions. So from that we will be able to, that is the solubility what we will get, that is the molar solubility. So from this molar solubility we will be able to, 1 mole means 283, and from this with the 100 milliliter of the solution how much it will be there, that will be, we have to calculate. So this option will be C, that you can do it yourself. And that is all for today's lecture. So in this is the last lecture in the ionic equilibrium, and I hope you understand all the things. If you like this video, you can share to your friends. Thank you very much for watching. Thank you.